Section 4.2, we were talking about prime and composite numbers, and we had ended our last session, class session, with a very interesting fact that should help us make a decision about whether a number is prime. And the fact that we ended up with is this one. There we were. That if we're testing to see if a number is prime, we know when we can stop testing. We can stop testing at the square root of that number. So the example that I gave was the square root of was the number 143. And if we wanted to know if 143 is divisible by anything, that is if it's a prime or composite, we can take the square root. We get 11.95, roughly. And we can test all the prime numbers that are smaller than that, and that's all we need to test. So we could test 2, 3, 5, 7, 11. And if we tested all of them, of course, if we tested them and they find out that it divides it, then that answered our question. But if we tested all of them and none of those numbers divide 143, then we know that 143 is prime. It's a really handy fact. Otherwise, you'd have to see, what about 13? What about 19? What about 23? How do I know when to stop? Well, this is how you know. You can stop that soon. So we're going to do the example with 967. So the question says, what is the greatest prime you must consider to test whether this number is prime? So how do I do that problem? I do. I take the square root of 967. So I need an approximation for the square root of 967. A couple decimals is fine. Doesn't really matter. 31 point what? 4. All right, that'll work. 31.4. Now, if 1, 4?
No, just 1. 31.1.
Okay, sorry. 31.1 it is. 31.1. If you answer 31.1 on this problem, you didn't quite answer the question they asked. You used the right theorem, you just didn't answer the question they asked. The question they asked is, what is the greatest prime you must consider to test whether 967 is prime? And 31.1 is not prime. Prime only applies to whole numbers. We can only talk about whole numbers being a prime number or a composite. So what would be the answer to the question based on this work? What do you think? It would be 31. Now, it's not because 31.1 rounds down to 31. Not exactly anyway. Why would it be 31? I mean, what are we looking for when we're asked that question?
It's the biggest prime number closest to this square root of 967.
Right. So 31 is the biggest number, period. That's the whole number closest to this one. And it happens to be also prime, right? So that's how we know that we can stop at the 31, is because 31 is the biggest prime that is underneath 31.1. You guys with me? So on this question over here that we did the other day, if the same question were asked, the answer would be 11, because it's the biggest prime closest to this value. Now let's say, for instance, that I did the square root of 147 over here. So what do you get when you do square root 147? 12.12. So just rounding 12 down to 12 would not be a good answer for this, right? Because 12 is not prime. The answer for this would still be, the biggest number to test would still be 11. You guys with me? I don't want you to think we're just rounding down. That is not what we're doing. We are rounding down, but we're rounding down to the nearest prime number is what we're really doing, which is a little bit different way of thinking about rounding. Okay, let's do a couple other examples. We talked about last time this interesting definition. In fact, let me go back to the definition this references just to remind us, since it was last time. Not definition, theorem. We had the fundamental theorem of arithmetic that said each composite number, right, numbers that aren't prime, can be written as a product of primes in one and only one way, except the order might be different. Okay? Saying that there is a unique way of getting a prime factorization for a set of numbers. So let's take a look at this example that references that fact. It says, show that if the number 1 were considered prime, because we talked about it last time, that's one of those sort of questions that people have sometimes, where does 1 fit in? And the answer is nowhere, doesn't fit in anywhere. All right, if 1 were considered a prime number, then every factorization would have more than one prime factorization. Okay, so I'm going to use a very simple example, very small number in our discussion. We're going to use the number 15. How in the world could I break 15 down into factors? 3 times 5. Does that work for everybody? Okay. We would say that that is the prime factorization because 3 and 5 are both prime, correct? Okay. If, however, 1 were considered to be a prime number, what else could I break 15 down into that would work with prime factors?
15.
Well, 1 and 15 wouldn't because 15 is not prime. But 1 times 3 times 5 would work okay, wouldn't it? I mean, it is a factorization for this. And if 1 were prime, then I would be able to write down 1 times 3 times 5. What else would I be able to write down? Right? 1 times 1 times 3 times 5.
So it'd be like infinite.
Yeah, I'd have infinitely many ways that I could write a prime factorization if the number 1 was actually a prime number. So just from a practical standpoint, not a definitional standpoint, but from a very practical standpoint, we do not want the number 1 to be prime. We really want this prime factorization to be unique. It's a very helpful fact, okay? So that's another reason why we like the fact that 1's not considered a prime number is because it would mess this other pieces of information up and what we want to do with them, okay? And this is it. This is showing if we had the number 1 that was prime, we'd have multiple representations for the number 15 that would all be prime representations. Okay, so this actually does, in fact, show what we're supposed to show. All right. Mr. Arbor. Mr. Arbor wants to plant apple trees in a rectangular array. We talked about that in the last chapter. If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. So can you picture what the problem's doing? Can you see it? I don't really want to draw 36 of them out, but I'll be happy to draw a few of them. Let's say we had 9. I want 9. How about we have 6? 8's better. Let's do 8. Okay. I know I keep changing my mind. I could have, with the number 8, I could have 2 rows, and there would be 2 rows of 4, right? Or I could have 4 rows of 2, or I could have 1 row of 8. That would work with the number 8. Agreed? Okay. If I wanted to do the number 9, that's an even better one, maybe because I've got another option here. Let me do this. If I had the number 9, I'd have a possibility of having 3 rows of 3 each. Right? This is what a rectangular array would look like with my trees. Now, my example doesn't have this. It actually has 36. So with the number 36, how many rows of how many trees could I have?
6 or 6.
Okay, so I have one option is be 6 and 6. Let's just write down the factors that I could have. 6 times 6, what else do I have? 3 and 12. Okay, someone else.
4 and 9.
4 and 9. Okay. What else?
Yeah, 1 row. 6.
You could have 1 and 36. Technically, that would be considered an array. There's 1 missing. 2 and 18. These are all the different factorizations, not prime factorizations, but factorizations for the number 36, right? So let's answer the question now. It says, find all possible numbers of rows if each row is to have the same number of trees. So how many rows could I have? Well, let's just go in order. I could have 1 row of 36. I could have 2 rows of 18. I could have 3 rows of 12, 4 rows of 9, 6 rows of 6. I actually could have 9 rows of 4. This starts to feel a little bit like we're sort of, backtracking, but we are. 9 rows of 4, or 12 rows of 3, or 18 rows of 2, or 36 rows of 1. These are the number of rows I could have. This is a really good example. And I sort of want you to flag it in your mind, because at some point we're going to be, I can't remember, but it's coming up soon, a couple weeks maybe, we're going to be picking out presentation sections and so forth for your presentation at the end. This is a really good application, both in this section and in the next section as well, of how this least common multiple, greatest common divisor thing, which we're about to get into, can use factorization in a concrete way. We have to know the factors in order to be able to create this rectangular array. Okay? All right, last example. Whoops. Trying to move things around and everything went crazy. Bob. Bob says that he wants to check whether a number is prime. If he wants to check whether a number is prime, he checks the divisibility rules for 2, 3, 4, 5, 8, 10, 6, 8, 10. Sorry. He says that if a number is not divisible by these numbers, then it's prime. How do you respond? There's several things that we might want to say to Mr. Bob.
What about the number 49?
Okay, so that's our first problem. The first problem, directly in contrast to what he's saying, is 49 is not divisible by these numbers. But 49 equals 7 times 7, hence is not prime. So we call 49, in this case, a counterexample. It's an example showing that his method does not always work. Notice, we could word this question a little bit differently, that it would be a true statement, kind of like the last example you guys did that I was talking about when I was talking about your homework. We could say something like this. Bob says that if a number is divisible by 2, 3, 4, 5, 6, 8, or 10, then it's not prime. And then Bob would be right, right? That would be a true statement. But it's not enough to test with, right? There's other things that could happen. There's also something else weird going on here. So his statement is flat out not true, but it's also a little bit overkill. If you were to have already tested the numbers 2 and 3, we don't need to test by 4, right? There's no reason to test the number 4. If the number 2 didn't work, the number 4 is certainly not going to. Same for the number 6 and the number 8 and the number 10. He's testing things that he doesn't need to test. He's doing more work than he needs to do for the numbers he even did pick. Agreed? So the other issue, and this isn't really directly addressing his problem, but it is something to be aware of, is that testing, in this case, the numbers he tested that were unnecessary were 4, 6, 8, and 10. Testing isn't necessary or isn't needed because what is true about 4, 6, 8, I didn't mean 9, 4, 6, 8, and 10? They're even. What else could we say about them in terms of this section of material? Okay, something else. What kind of a number are they? Composite's the word I'm looking for. The issue is that they're composite. There's really nothing special about them being even. Like if I used the number 9 in this list, it would also not be even, but it wouldn't be needed because 9's also not prime. So 4, 6, 8, and 10, the reason is because 4, 6, 8, and 10 are composite. Again, if a number is divisible by one of them, certainly that tells me that the number is also composite, but so 2 would have already told me that, right? If it's divisible by 4, 6, 8, and 10, it's also divisible by 2, and I would have already known that that number didn't work anymore. You guys with me? All right.